So, what is optics? Well, it relates to the study of light, how light is produced, and how is it propagated, how do we measure it, and what are the properties, and how they interact with matter as well. So, why is optics important? First and foremost, the fact that you can see this is because of your eye, and that's the working of optics in your eye. A very simple, natural optical instrument here that you have. And of course, every one of you uses a handphone, and we love taking pictures with our handphone. They're beautiful. Well, this is an example. Now, it's not just a simple lens, and you collect the image and you let the image fall onto the image plane, and and it is image. It is actually made of a system of lenses here, and it's quite complex actually. And of course, it is also important because it's used in communication. Optics is needed in communication, and how it works. Fiber without optics, we wouldn't have the internet as you know today. The ease of getting information, and at times too much information. Okay, now first, uh, we give you for this particular lecture. Basically, we are going to cover an overview of optics. We're going to discuss a little bit about nature of light, and we will talk about how to produce it, how to measure light. Okay, in what we call chapter 1. Now, the overview optics. We are going to start with ray optics, and this has to do with or sometimes it's called geometrical optics. And this optic here is concerned with it is applicable whereby your light wavelength is much smaller than the object you're viewing, than the aperture that you let the light pass through. So these aperture sizes are very large compared to the wavelength. And in this case, we ignore diffraction, and basically we just follow the ray. And these rays obey a set of geometrical rules. Okay, so we just focus on the location and the direction of light rays. And next we go into wave optics. It is simplified scalar wave theory, and this can describe interference and explain how interference occur. That gives you those beautiful fringes, and how diffraction occurs. And in this case, we will look into, rather, it would be a review back. To check you test your memory maybe. We're going to talk about phase and group velocities of light waves, okay? And then next we'll go to electromagnetic optics. So in this case, we will have to consider the vector field, and here we will be focusing on polarization of light. Of course, then there's another set here, which is quantum optics, or sometimes called photon optics. And here it will describe the optical phenomena that have quantum mechanical characteristics. But we will not be covering this because this is not within our syllabus. Let's compare ray and wave optics. Now, for ray optics, you'll find that that's applicable when the wavelength of light is much shorter than the dimension of the obstacle, or even the aperture. And when the wavelength is comparable to the size of the dimension of the obstacle or an aperture, then you find, or maybe even larger than that, then you find wave optics is applicable. And for your course content, you will find that, and I hope you have done methods. One, vibration and waves, because these courses, what you learn there will be helpful for you here. And this course will be made up of 40% continuous assessment, and you're going to have 2 tests, 5 to maybe about 6 tutorial. Minimum is 5 exercises or quizzes, about 2 assignments, and you will have 60% come from your final exam. And the main text will be Introduction to Optics by Pedrotti, and Pedrotti. Some of the relevant chapters have been uploaded into Spectrum for your reference. So please do read those chapters. It will help a lot. And this is briefly the synopsis of your course. We will be starting on introduction here, and then we'll go into ray optics and then into wave optics. So let's start with introduction on nature of light. Is it a wave or is it a particle? We'll start with the initial study of light by Isaac Newton. Here, he said that rays of light are very small bodies emitted from shining substances. So this is a corpuscular nature of light, gives a particle nature. And he concluded that light appears to travel in straight line. Well, that's what he saw from these sharp shadows cast by light being obstructed by an obstacle here. But it cannot explain the formation of Newton's ring. This is Newton's ring. Then Christian Huygens, he started to explain about light having wave properties. He said that light is a wave motion that spreads out from the source in all directions. So in terms of Huygens' principle, he has these wavelets which are basically starting from points that are on a wavefront, and each point on the wavefront can be taken as a new source of wavelets. So you have these wavelets that is going to propagate out as time progresses. And this principle was using this principle, we could explain interference and diffraction, though not perfect, but it could explain. And using this principle, he could actually derive the laws for reflection as well as refraction. Here is Huygens' principle. Now, for plane waves, it will look like this. On the wavefront at time t here, we take a sample of 4 points here. Now, each point here will act as a secondary light source, and it will emit a spherical wave that will travel in all directions. And at time delta t later, it will travel distance of c multiplied by time, and by drawing a line that is a tangent to all these wavelets, surface of this spherical wavelets, then we will get a new wavefront. So from there we can then look at how this wavefront is propagated in time. And for the case of spherical wavefront, similarly, the same thing. We can think of the wavefront as made up of many points here, and these become secondary sources of wavelets, which at time delta t later would have traveled up to here by drawing a line that is a tangent to the surface of all these secondary wavelets. We will get the new wavefront. So That's how he thought of how light. The visualization perhaps you can think of it as like in a still water, pool water in a lake. You drop a pebble, and then you see these ripples that propagate outwards. Here we are still on wave nature of light. Here are two proponents for wave nature. We have Thomas Young. He gave us the Young's double slit experiment in 1803, and this confirmed the wave nature where he saw fringes which could be explained only when light is when we treat light as a wave. And then we have Fresnel, and in 1821 he proposed that light is a transverse wave. And here we have another proponent for wave nature of light. We have James Clerk Maxwell, and he came up with the four famous Maxwell equations, and he worked in the field of electromagnetism, and he predicted the speed of EM wave. And visible light is actually is an electromagnetic wave. As you can see here, we have the E field in red, the B field in blue. The plane is orthogonal to each other and is propagating in this direction. And here gives the electromagnetic spectrum of the entire spectrum, whereby light, visible light, is from 380 nanometer at the shorter wavelength range up to 770 nanometer. Here are the proponents for particle nature of light from quantum theory of light pioneered by these three gentlemen here. We have Max Planck. He gave us the energy equals to h multiplied by the frequency of light. And then we have Albert Einstein, who explained photoelectric effect. And then we have Niels Bohr, who gave us quantum of radiation in the hydrogen atom relating to emission and absorption. And EM, that is electromagnetic energy, is quantized. And there's a name given to it called photon, which was given by Gilbert Lewis in 1926. And hence, how do we link wave and particle together? Here comes de Broglie. He gave us the hypothesis that it is a particle with more than P would have an associated wavelength lambda, which is equals to h Planck constant divided by P. And his hypothesis was actually confirmed experimentally a few years later, about 3 to 4 years later, by Davison and Germer, as well as Sir George Thomson in England. So there you have. We have the wave-particle duality of light. It can behave like a wave, and that helps us to explain interference and diffraction. And it can behave like a particle, especially when it interacts with matter, for example, the photoelectric effect. Okay, those pioneering works were awarded Nobel Prize to this great scientist. In 1981, Max Planck won the Nobel Prize in Physics in recognition for his discovery of energy quanta. In 1921, it was awarded to Albert Einstein, especially for his discovery of the law of photoelectric effect. And then next we have in 1922 to Niels Bohr for his investigation of the structure of atoms and of radiation that emanated from them. And de Broglie, he provided a link between the wavelength to momentum. So he actually discovered his discovery of the wave nature of actually it was given for electrons. So in other words, wave particle duality also applies to electrons. Electrons actually usually behave like particles, which we can see as point light scintillating spots of phosphor on the phosphor screen. But they also behave like waves, especially as manifested by the diffraction in the electron microscope. So, what are the differences between electron and photon then? Photons obey Bose-Einstein statistics, which tells you that identical photons with the same energy and momentum, they can exist together in very large numbers as well. But in terms of electrons, then they obey Fermi-Dirac statistics, which tells us that no two electrons in the same state can have precisely the same physical properties. And here are some relation and other difference here. You'll see photon has zero rest mass. Electrons has rest mass. Some rest mass, a small number though, is to the power negative 31 kilogram. And to find the momentum of photon is equal to its energy divided by its speed, and the wavelength is associated through de Broglie's relation, and the speed for a photon is equals to a constant value c here. And for electron, if it's traveling at speed close to the speed of light, then we have to take into consideration the energy associated with its rest mass here in the momentum, wavelength, as well as the speed here. So this is a simple calculation which you can follow through to see what's the difference if we apply it to a photon and we apply it to electron. So you find that for an electron that's traveling close to the speed of light, then the moment here the common thing between the two of them is that they both have the same energy. In terms of the electron, it has a kinetic energy of 2.5 mega electron volt. For the photon, it would have the same total energy, which is also 2.5 mega electron volt. So how would their value of the momentum, their wavelength, and speed be? So for that electron, we calculated is 1.58 times 10 minus 21 kilogram meter per second. The wavelength associated with it would be close to 4.2 or 19 times 10 to the minus 13 meter, and the speed would be 2.95, slightly short of the speed of light in vacuum. In the case of a photon, these are the values: 1.61 here, which is higher, 4.12 is shorter, and this is, of course, the speed of light in vacuum, and that's 3 times 10 to the 8 meters per second. Okay, next, let's look into the electromagnetic spectrum. Now, light, as we have shown earlier, it's identified as an EM wave. So it is in the frequency range which our eye can detect. And I've given you the range earlier on. Now, EM wave, I have also shown you that we have this E and B field which is varying with time. And EM wave can be produced by accelerating charge distributions. It carries energy and it can exert forces on charged particles when they impinge on it. Okay, so in free space, all EM waves travel with the same speed. That is 3 times 10 to the 8 meters per second. And the frequency of EM wave then is determined also and is related to the speed and is related to the wavelength as given here. Not this slide, but the next one, which is related through this expression here. Okay. When we say that the light is monochromatic, it's characterized by having a single frequency. If it's polychromatic, poly here means many, so it has many frequencies. And when we talk about spectrum, we are talking about the distribution of energy or distribution of wavelength or distribution of frequency of the wave. And the common units used for wavelength is in angstrom, which is 10 to the power minus 10 meter. In the visible range, usually we talk about how many hundreds of nanometer. That's 10 to the power minus 9 meter here. And for the infrared, usually we talk in terms of microns. That's 10 to the power minus 6 meters. Now, this is the second mention of the range for visible light. And this shorter range, the shorter end gives you the violet. The longer wavelength value is where the red is. And on the shorter side, beyond shorter than that, we have the ultraviolet, which our eyes cannot detect, and the infrared, which is longer than beyond the end of the visible range. We have the infrared, which we can feel as heat actually. Now, most atoms and molecules, they have resonant frequencies in this optical range here. So the M wave in this range will then be able to interact very strongly with the atoms and molecules. Okay, now let's look into production and measurement of light. In order to produce light, then we would need sources of EM radiation. In order to detect, of course, we need detectors. And how do we classify them? We classify them in terms of their spectral sensitivity. In other words, what is the spectral range that they are able to detect, or what are the spectral range that these sources are giving EM radiation, the range of wavelength that they are able to give out. So we're talking about distribution of the wavelength. And secondly, we also talk about its what we call intensity or the strength. All right, so let's first look at the spectral range, which you can see here. So we're talking about variation in wavelength or variation in frequency. So the distribution in terms of wavelength and frequency. So it can, for the optical spectrum, we would mean from UV to visible to infrared. And these are the common units as we have looked at in, I think, about one or two slides before this. And then in terms of variation of strength, in terms of intensity, then we have to consider whether we are going to measure in terms of radiometric units, which is given here, or in terms of photometric units, which is here. Now for radiometry, it is the science of measurement, metry, of EM radiation. So it applies to all radiant energy, all wavelengths. For photometry, it applies only to the visible region whereby our eye can detect. So in other words, we will have one more factor to consider here, which is how the range in which our eye can respond, and our eye respond differently to different colors as well. And the peak response is in the yellow-green region, which as you can see here, this curve here tells us the response of eye to different colors. And at about 5:55, which is around here, our eye respond very well. In terms of units, for radiometry, we use radiant energy or radiant flux or power, radiant excitance or irradiance. Basically, the units that we use will be for radiant energy is watts second. For radiant power or radiant flux, it is in terms of watts. In terms of excitant, this is light being able to be reflected or being scattered from a surface, we're talking about watts per meter squared, or it is light falling on the surface, that means the surface being irradiated, so we call irradiance, is also in the units of watts per meter squared. And if we talk about radiant intensity, then we have to consider the solid angle, so that would be in the unit of steradian, watts per steradian. Now, the photometric counterpart would be for radiant energy, we will have luminous energy. But in this case, we talk about lumens second. In terms of luminous flux, we talk about lumens. In terms of luminous excitance or illuminance, we talk about lumens per meter squared or lux. Now, here are the old units. Now, if you look at here in terms of where is this lumens here or luminous intensity, we can talk in terms of lumens per steradian or candela. And here, CD here, short form abbreviation here is candela. So these are the old units. Now, how do we convert radiometric units to photometric units? Okay, there was mention about solid. Let's look at solid angle first, all right? So now, let's start with radiant intensity here in radiometry. We have one of the energy component whereby we talk about radiant intensity, and it's defined as the radiant flux emitted per unit of solid angle by a point source in a given direction. So this is a point source, is radiating light energy outward, and here in this particular direction here, this would be the central, going to the center, this direction here. We would like to measure the amount of flux that passes, that cuts across a certain surface that is subtended by what we call a solid angle. So what exactly is solid angle? Now, I've made a cone here, okay? So this would be our, what do you call it? The source, the point source, and this would be the cone, and this cone here subtend a certain angle, and then it has this area that's basically, you can think of the ice cream that you like to eat here that's placed on top of the ice cream cone. So this define the solid angle, okay? So if we have a point source of radiant power that is radiating uniformly in all direction, so the total for this particular sphere here, the total amount of solid angle here would be equal to 4 pi, and that's considered 4 pi, and the unit is steradian. So the radiant intensity then would be the radiant flux or the radiant power divided by 4 pi. Here, 4 pi. Now, how do we define solid angle? The unit that we use is steradian. Now, here I have a slide that explains it. So, to define 1 steradian, it would be equal to the area. This would be part of the sphere. So, the area on the sphere, so the surface here, that is equal to the square of the radius, this radius here. So here, the area here is r squared, and this distance is r, which you can see here, okay? So that would be equal to 1 steradian. In short, we write as SR. It is basically a three-dimensional analog of an angle. In terms of angle, it's just two-dimensional. So in that case, it will be visualized as being the angle that is subtended by a cone rather than just two lines on a flat piece of paper, but now it is a cone. That's solid angle for you. Now, here we would like to define inverse square. What is meant by inverse square law here? Well, let's look at a point source of light here. We have the power or the flux, the radiant flux, leaving this point source in all direction. And if we define a particular solid angle of area A, so this area A, so as it increases in distance further away, this surface, this area here is going to grow larger because this cone is going to subtend more, so then the surface will be larger. As you can see here, if the distance is double, the area will be quadruple. If the distance is tripled, the area would be 3 to the power of 2 times that of this area. Okay? So, in other words, what we have here is now the irradiance of the light from here falling on this surface. So the light, the irradiance of light falling onto a point on a spherical surface then would be equal to the total flux divided by this area. So that would be the irradiance. And the flux is actually equals to 4 pi multiplied by I here, which is the radiant intensity, divided by the area of this surface, which is equal to 4 pi r squared. So in other words, the irradiance is actually equal to the radiant intensity divided by r squared. So you find that it is actually following inverse square law. So as the distance increases linearly, the irradiance will then drop to the power of 2 square law. You have a square, inverse square law here. So it will decrease inversely with the square of the distance, in other words, to put it precisely. Okay, just now I was telling you that we would like to relate photometry to radiometry, right? Now, photometry, just now we were talking about radiometry, now we come to photometry, and we need to take the response of a human eye. So this is the curve of how the spectral response of a human eye. We respond very well at 555 nanometer. So looking at this graph here, or this diagram here, you'll see that equivalent to in terms of watts, actually, for 1 watt, we would have an equivalent of 685 lumens here. So let's look at the next slide. Or before we go there, you will find that during the day, which is photopic vision, our peak sensitivity is at 555 nanometer. But at night, our peak sensitivity shifts to slightly shorter wavelength, which is 510, which is over here. Now let's look at the next slide to see the conversion here. How do we convert? Now let's say that maximum luminous efficiency actually occurs at 555 with a luminous flux of 685, and this actually corresponds to the radiance flux of 1 watt. This here corresponds to the radiant flux of 1 watt. Okay, and so if you choose a wavelength which is not at the peak sensitivity, which is a 610 nanometer, let's go back to this slide here, 610 nanometer, that is equivalent to a luminous efficiency of 0.5 here. Okay, so let's go here. So that's 50%. So in other words, for 1 watt of radiant flux, we would be able to respond to it as if it's only 342 lumens. So there would, in terms of photometric unit, in other words, we would then have a K factor here, which is called the luminous efficacy, and that is equivalent to the maximum response at 685 flux, which is equivalent to a radiant flux of 1 watt, multiplied by the efficiency. All right, let's try an example to understand that. Let's say we have a light bulb that's giving out 100 watts of radiant power, and it is at 2 meters from a surface which is oriented perpendicular to the line from the, let's say we have a source, a bulb, and a surface, and this line perpendicular to the surface, and it is 2 meters away. So find the irradiance at the surface. Now, if all the 100 watt is emitted from the bulb, and this bulb is emitting at 650, is a monochromatic light source, so it's 650 nanometer. So the irradiance, as we learned, is equals to the flux divided by the area. Now, we talk about a bulb being a point source, so the total area would be the area of the sphere, whereby the radius is 2 meters away. This is a point source, 2 meters, so the radius, the area is the area of the sphere, which is 4 pi r squared here. So it's 100 watt divided by 4 pi 2 squared. So that would give us approximately 2 watt per meter squared in radiometric reading. Now we want to change this to illuminance. So how do we do that? Now from the CIE curve, you will find that at 650 here, the efficiency is only 0.1, which is 10%. Okay, so therefore the illuminance then would actually be 0.1 multiplied by the irradiance, 0.1 of 685, right? Multiplied by the irradiance, that will give us 137 lumens per meter squared or less. So that would be our photometric unit. Okay, let's stop here. So this lists down what we've learned so far for this lecture. Do look through this and see if you can answer all this. Okay, if you are able to do all this. Thank you very much.